All right. Hello, Physics 135 students. And this is apparently class number 13. A thousand pardons. I evidently did not make this recording last week. So nevertheless, we're going to make sure that we have this recording made and posted so that you all can take a look. Hopefully you were able to see the slides already. So first, for the icebreaker question, this is regarding uh, really thinking back on this semester of all the material we've covered. What rock band group would you name if you had to name something? And for myself, I am admittedly not a super creative person, but I think that as far as a rock band group, Quasar would be a pretty good one, or maybe the first 3 minutes, which of course is the title of this class, not super original. So go ahead and try to think of your own possibly creative title, possibly not so creative rock band group, and go ahead and post that in the Discord if you'd like to, and ideally also email me. Now, yeah, it's again quite unfortunate that I did not evidently record and post this the previous week because it was rather timely. Artemis 2 is now finished, but it was successfully launched April 1st at 6:24 p.m. Eastern Time. I was watching this event live, not in Florida, but I was watching it on TV live, and I was very anxious and excited and nervous. And it was really, I have not had a chance to witness anything really with respect to, the space age going to the moon. In fact, no one has been able to witness a comparable event like this in over 50 years now. So, regarding this April 1st launch, you might have remembered earlier in the semester I was discussing how the original launch date was in March. Well, they found some issues with the heat shield, which they had to iron out really for reentry more so than for launch. On the launch day, they also were checking things out, had a few minor things, but all got resolved. One thing that was a little bit more major was that the only functional toilet on board was non-functional for a period of time, but they did also get that sorted out. The astronauts had to get that sorted out since it was after launch, actually. They also had a communication partial droppage where the I believe it was the astronauts were not able to hear what Capcom in Texas was sending out, but the other way was fine. And that was just brief. They don't really entirely understand why there was a brief outage, but that all worked out fine. And again, this is not relevant anymore. Um, but they went through a series of different moments. The countdown to launch was one major moment where they could have called abort if it seemed like there was a more major mishap rather than minor mishaps that were resolved. They also had to check all their systems before they did like the last major burn for making sure that they had the right orbital trajectory for getting to the moon. And they did do that, and they completed their mission. They successfully splashed down um, just a few days ago, actually. And then on Saturday, or no, excuse me, on Friday. And then regarding Artemis 2, okay, so this was not a mission for landing on the moon. And for that matter, we already have landed on the moon back, in the 60s and 70s. So what is the point of Artemis 2? The idea is this is really a step towards going back to the moon, but not just about walking on the moon again, but setting up a permanent lunar base, just like we've had a permanent base in Antarctica. Not just the US, but all the world scientists basically have access to that now. We've had that for quite some time, and then we've had a continuous presence on the International Space Station for 30-ish years. And regarding setting up this permanent moon base, it's kind of important for helium-3, which has been depleted on the Earth, which is pretty important for fusion experiments, for example. It would be quite helpful for that and a number of other scientific studies. And this is also one step along the way to Mars. All right, so yeah, the last time astronauts walked on the moon was in 1972, and that was 54 years ago now. And for actually walking on the moon, that's meant to be Artemis 4. It was originally meant to be a trilogy, but they decided to do a little bit more setup for the moon base in Artemis 3 and then walking on the moon in Artemis 4. And one special part of Artemis 2 was due to the trajectory going around the lunar far side with a pretty elliptical orbit. This was the farthest humans have ever been away from Earth. And again, we're setting up not just a moon base, but really a permanent presence on the moon, like we've done in Antarctica and the International Space Station now. Okay, so for today, again, hopefully you all were able to see these slides, but idea is that we're going to be learning about radio astronomy. So we have three initial goals for learning. First, why did Carl Jansky find that there was some really unknown hiss or noise that repeated every 23 hours and 56 minutes instead of every 24 hours? Second, we're going to discuss the um, really detection of radio waves from the sun, which was impacted or maybe assisted in some ways by a major global event that happened in the 1930s. Third, we're going to talk about the debate about radio sources and how this was finally resolved about whether they were stars or galaxies. So first, for Carl Jansky's experiment, in 1932, Carl Jansky was working for Bell Labs. This hopefully sounds familiar given Penzias and Wilson's discovery of the CMB a few decades later. Um, so in 1932, the issue is that Bell Labs was finding some mysterious hiss or noise in their transatlantic radio telephones. And so they deployed a scientist named Carl Jansky to figure this out, who worked with this huge apparatus. It's a radio antenna array. And the hiss was at 20.5 megahertz. At radio frequencies, we don't typically talk about the wavelength as much. We typically more of go for the frequency for just historical reasons. And then regarding how this apparatus worked, it was again a big apparatus. They used Ford Model T tires in order to move part of it around, really just rotate. It wasn't otherwise very mobile. And what Carl Jansky found is that this mysterious hiss peaked 4 minutes earlier each day. It wasn't on a 24-hour cycle, it was a little bit offset. And so this means that that signal could not be coming from the sun, but instead, what it really meant with the 4 minutes earlier each day is that it was related to the stars. And that is because the stars rise and set, or at the very least, not all stars rise and set, as you'd learn in Astro 100, the solar system, but at the very least, stars have a periodic motion on a 23-hour, 56-minute cycle. And this is because as the Earth rotates, it also revolves around the sun. So the Earth, sees the sun on a periodic 24-hour cycle due to the rotation. But because of the revolution, the stars show up a little bit earlier each day. And Carl Jansky found in particular that the direction of this hiss was strongest in the direction of Sagittarius, which is towards the center of our galaxy. And as unfortunately, after Carl Jansky found this out, Bell Labs really didn't care about astronomy. Of course, they're a company related to telecommunications on the Earth. They reassigned Jansky to some other project we don't really know, or maybe some historians have figured out now. But radio astronomy was quickly forgotten. But nevertheless, this was the first really discovery or experiment related to radio astronomy. a few years later, a amateur astronomer named Grote Reber built his own radio telescope. This is pictured here, Grote Reber's backyard. So I think Grote Reber was an engineer and probably built this himself, but very cool, I'd have to say. And I guess I should mention this is in the Midwest in Illinois. Maybe one of the reasons why Grote built a radio telescope instead of a regular telescope is it's a little bit hard to see, but there are a lot of clouds here. Radio, you can see right through the clouds, so it kind of doesn't matter. And um, Grote Reber took his radio telescope. It was the world's first parabolic dish, so kind of like the same-ish shape as like a visible light telescope to bounce the radio waves instead of using an antenna like Carl Jansky. And Grote Reber used this to look at the radio brightness all throughout the Milky Way and found that the Milky Way was brighter in radio waves, just in the same kind of distribution of where the stars are brighter as well. And then he also found that there were some individual sources that were brighter than the kind of Milky Way background uh, radio waves. In particular, certain sources in Cygnus and Cassiopeia appear to be quite strongly emitting in radio waves. A couple of years later, sorry, not the 1930s, but 1940s, during World War II, especially after aircraft started getting involved, there was an issue in London where they had anti-aircraft radar, but there was some interference that was causing issues with their ability to handle the bombing and to put out alerts, etc. And so the British Army asked a man named Hay to look into this, and Hay found that the noise, in this case, did have a 24-hour cycle. In particular, it was correlated with the position of the sun. And so, in other words, we found that the sun itself emits radio waves. In particular, the sun is most active in the radio wavelength when there is some sort of solar activity, whether those are sunspots or even more particularly when there are really strong solar flares. So the same sort of stuff that causes the aurora on Earth causes the sun to emit more radio waves. And although this was discovered during World War II, it was classified by the British Army. It was probably shared with the Allies, but it was not fully declassified until after World War II ended. And so then after the war, people started to debate really what were the sources of radio waves because now that people knew that it wasn't just the Milky Way as a whole, but the sun emits radio waves too, some people thought that uh, the radio sources were that in the Milky Way were kind of like stars, where with a low resolution viewing, like just with our eyes, we can't tell that there are individual stars that make up that Milky Way. Whereas when Galileo pointed his telescope at the Milky Way, he did find individual stars. So one of the early radio astronomers, Martin Riley, believed that same sort of thing. If we had a good enough radio telescope and we pointed it around the Milky Way, we would end up finding that just all the radio sources are stars. They're just more diffuse in radio waves, and radio telescopes were not very, are for one thing, just very difficult to have high angular resolution due to the long wavelength, and they weren't super sophisticated back then. On the other hand, some other scientists and researchers in radio astronomy thought that really the sources for these radio waves were largely distant galaxies. And although that we had measured radio waves coming from the sun, the other stars were going to be far too faint in radio waves for their great distances, even within the Milky Way, for us to be able to detect them, except for maybe some of the nearest by stars. All right. And then this mystery was eventually resolved by a pair of astronomers, Bode and Minkowski. This is a different Minkowski, I should say, than the one that was involved in the development of general relativity very shortly after Einstein published. And they were using the Palomar telescope. It was the world's largest telescope at that time. 200 inches is the mirror's diameter. And they used that, and I should mention that this is the same telescope that Edwin Hubble was using. Um, and they found the location of Cygnus A, one of these radio sources, and found that it was, in fact, a distant galaxy about 700 million light years away. And so they were doing this, again, in the visible, because in the radio, we couldn't really determine, whether it was a star or galaxy. But there was a very strong spatial overlap, and therefore they were able to put this mystery to rest. And in terms of why these galaxies are shining so bright, the radio waves, these are called active galactic nuclei. So they are compact sources. We'll talk about what those are in a moment. So first, let's go ahead and check back in for our attention checks. So for this first one, we've talked about this now. The reason for the 23-hour, 56-minute cycle is because Carl Jansky's radio hiss was coming from a sidereal source. In other words, something that is related to the stars or beyond our solar system. And then regarding this major global event, so this was 1942, is World War II. And then third, for the radio star hypothesis, the reason why this was eventually disfavored in favor of galaxies, it's not that the sun is the only star capable of emitting radio waves. Other ones are too, they're just kind of too faint. Really, the answer is B, regarding Bade and Minkowski's discovery using optical telescopes to um, find co-spatially what the sources of radio emission were. I mean, if they were stars, then with a large enough telescope within our Milky Way, we would notice that it's a star within the Milky Way. Instead, they found that it was a distant galaxy. All right, now in terms of better understanding why these distant galaxies are such bright radio sources, first let's kind of break this down because there are actually two main types of radio sources in astronomy, although they're related. First are so-called radio galaxies, where these are, unlike the Milky Way, which is a spiral galaxy, these are massive ellipticals, and they produce a lot more radio emission due to jets and different features. Um, Ultimately, arguably, the elliptical galaxies owe their radio emission to something that's kind of like a lower luminosity version of a quasar. So quasars were discovered in the 1970s, and these were originally standing for quasi-stellar radio sources. So this was an acronym like LASER, but now it's not really used as such. And for these quasi-stellar radio sources, they look like stars. They appear point-like, but we now know that they are really the sites of intense supermassive black hole accretion that emit really strong jets. And so these are some of the brightest objects in the universe. So, in other words, basically the same thing. We think they're supermassive black holes that power both cases, but for quasars, they shine much brighter. Radio galaxies, there's less activity. All right, and then in terms of quasars, in the Big Bang Theory, as we talked about in terms of a more recently recorded lecture in our 14th lecture, in the Big Bang Theory, unlike the steady state theory, as space expands in the Big Bang Theory, galaxies are changing with time. We expect that the universe is becoming kind of more and more red and dead, or more and more diffuse with time. And since the universe is becoming more diffuse, that means that the galaxies are fed less with gas, so they should have less activity or be less energetic as the universe ages. Whereas for steady state theory, we'd expect a uniform distribution of quasars as new galaxies fill in these voids. On the other hand, observationally, we simply only find quasars at high redshift, in other words, at the distant past. So this is um, really an issue of explanatory scope or explanatory power for a steady state theory, but very trivially explained by the Big Bang theory. And then just going back into what powers quasars. So again, the idea is that they're supermassive black holes. And then as pictured here, um, for these supermassive black holes, there is material that is orbiting around them at the center of these galaxies. And then with time, there's some material that steadily flows into a so-called accretion disk. And as this gas spirals in closer and closer and closer, the gas shocks due to the release of gravitational potential energy and gets really, really hot. So, in addition to radio waves that are primarily due to the jets, there's a lot of X-ray emission, actually, or in the case of supermassive black holes, it doesn't actually get that hot, more of intense UV emission still. Now, in terms of the feeding of these supermassive black holes, there's so much material and their masses are so large that they end up shining brighter than 1,000 galaxies. And although some material does flow through the event horizon that we never see again, some material ends up in orbits where they just barely miss. And so that's kind of like a gravity assist then. If the material just barely misses and kind of lies along magnetic fields that are oriented perpendicular to the black hole, then they end up getting ejected. These magnetic fields seem to be very collimated into, again, what we call a jet. And these jets are responsible for powering the radio mission as these really high energy particles that have been accelerated very close to the speed of light gyrate along these magnetic field lines. They produce radio synchrotron emission, and they also end up ramming into the interstellar or intergalactic or intracluster medium. All right. Uh, and then in terms of spiral galaxies, so in spiral galaxies, we have a lot of blue stars that form the spiral pattern. And these blue stars are evidence, as you learn more about in Astro 105, Stars and Galaxies, these blue stars are evidence that there is recent episodes of star formation. And in other words, there is a source for forming those stars, namely dust and gas. And for the reason why they're blue, it's because the youngest stars are the hottest, which peak in the UV or towards the blue side of the spectrum. All right, and this is material that's relevant for your worksheet. So go ahead and pause the video now and work on the first worksheet for attention check 4. Okay, hopefully pause the video. Now unpause. And next, we're going to start talking about the relationship between radio astronomy and the Big Bang. And so regarding the discovery of the CMB, I mentioned earlier that, oh, you should have learned about this already. Well, you should have read it about it in the book, but I guess I, of course, forgot that this was not recorded earlier. So we have 3 more goals for learning. First, what was the original purpose for the Holmdel horn antenna before it actually got used for radio astronomy? Second, why did Robert Dick of Princeton University tell his colleagues, well, boys, we've been scooped after hearing about Bell's Lab's result? And then third, there was a theorist who was excluded from the 1978 Nobel Prize, much to the chagrin of the kind of academic community, but was finally recognized in 2019. So which theorist was this? Okay, so first, regarding looking for the Big Bang's afterglow, a group at Princeton was really responsible for doing the detailed theory and calculations that predicted this. 1964, Robert Dick at Princeton University thought about George Gamov's and collaborators' Big Bang theory and thought that, okay, according to the Big Bang Theory, the very early universe should have been very, very hot. He called it a dense fireball. And one of his colleagues, Jim Peebles, performed the detailed mathematics and found that this radiation should have been cooled down today as the universe expanded, expanded, expanded. And it should be anywhere from like 3 to 10 Kelvin. They weren't exactly sure. It depended on how much time had elapsed since the Big Bang. And um, at this point in the 1960s, it's pretty well understood that the universe was somewhere between 10 and 20 billion years old, but they didn't really know exactly how old the universe was. And so Robert Dick, who is more of the principal investigator, um, asked a couple of colleagues at Princeton University, Wilkinson and Roll, to build a what's called a radiometer, so something like a radio telescope, in order to find the signal. Um, Wilkinson, we'll talk a little bit more later about a mission named after Wilkinson. So Wilkinson ended up getting some recognition for this work, although much, much later. Not the theorist, though. And so what they were looking for was really the afterglow from this dense fireball from the Big Bang itself. Meanwhile, so this was at Princeton University, at Bell Labs, totally unaware of what was going on at Princeton University. Arno Penzias and Robert Wilson, were kind of like Carl Jansky, were radio astronomers. And in contrast to Carl Jansky, they were allowed a lot more flexibility for doing their work. Um, they were doing this in Holmdel, New Jersey, and the original purpose of this radio dish or radio device was not really for astronomy. Again, this was a telecommunications company. The idea was to bounce radio signals across the Atlantic, but they were finding some noise, kind of like Carl Jansky. In this case, their noise was at 7.35 centimeters, whereas College Jansky's radio hiss was at 100 times longer wavelength. And interestingly, they found that the noise was not on a sidereal time, and it didn't have any apparent repetition, but it just seemed to come from all directions and to be this kind of constant hum 24 hours a day. And they had to first really make sure that all terrestrial sources were eliminated. At first, they thought that the antenna was picking up its own, like just heat noise that produces some radio waves. And then they also reported in their laboratory kind of notebooks that they submitted to Bell Labs, as well as eventually to their publication, that there were pigeons that were roosting in the antenna that were leaving behind some white dielectric material. So that's the professional way to say that there were pigeon droppings. Originally, they shooed the pigeons away. Pigeons came back. They brought the pigeons to a bird like sanctuary or bird person. The pigeons left the bird sanctuary and flew back. So eventually, they had to shoot them to really make sure that the pigeons were not the source. And still, the hiss continued. Um, Penzias mentioned this to a friend over at MIT, Bernie Burke, who was familiar with the Princeton work. Bernie Burke called Robert Dick on the phone and said, "Hey, you really have to talk to this guy, Penzias." And when Dick talked to Penzias and realized that they um, had found the cosmic microwave background over at Bell Labs, they were, a little bit bummed about that. Um, on the other hand, Penzias and Wilson, maybe as an act of good faith to not kind of trample over the Princeton group entirely, they played it very safe in their publication. Now, part of that is also maybe just that they were, not really as well versed in the Big Bang Theory. They reported their detection and they didn't associate it with the Big Bang. They left it to the Princeton group to write a subsequent paper that published on the theory about this. So, really, kind of, nice behavior by Penzias and Wilson to still allow the Princeton group ideally some credit. And so, in terms of attention check number 8, so this is a slightly different question than one of the other ones. What does it mean for the CMB his to be isotropic? And again, the idea was that it was isotropic means same in all directions. So answer is C. The signal was uniform in every direction across the sky. And then regarding why this is considered a safe publication, it's really because they were only reporting their measurements and they didn't provide any of the theory. So answer B. They did not wait for the Nobel Committee. They published first. Now, in terms of the Nobel Prize controversy, this is one of the quickest turnarounds, not the quickest, but one of the quickest turnarounds between discovery and the awarding of a Nobel Prize. And Robert Dick and Jim Peebles were not given the Nobel Prize in 1978, even though they played really a fundamental role. So this is kind of an instance where it seems like the Nobel Prize Committee really favors experimental physics over theoretical physics, somewhat unfortunately. And there have been numerous other instances of this. Now, in 2019, eventually, Jim Peebles, one of the original theorists, was awarded a Nobel Prize for his contributions. To quote it, understanding the evolution of the universe. So basically, for this theoretical work, it was kind of a funny or kind of odd time for Jim Peebles to be awarded, so to speak, because Jim Peebles was given half an award that was otherwise given for exoplanets. But this is, I guess you could say, the Nobel Prize Committee apologizing, if you will, or finally um, giving the theorist some credit. The Nobel Prize is not awarded posthumously, and so therefore Robert Dick was not able to be granted the award. Now, regarding the CMB, again, the kind of idea here, more from the Princeton group, that as the universe started out very, very hot and dense, it would have cooled as it expanded. And the model from Dick and Peebles was that this afterglow should still be visible today. It just wouldn't be evidently a fireball, so to speak. It wouldn't be in the UV or infrared or visible part of the spectrum. It would have been redshifted all the way into the microwave region by the expansion of space. And in the very early universe, we've talked about this before. Idea is that it was too hot for atoms. Eventually, um, the material cooled down, atoms were able to form, and then lights were able to freely travel. Before that, it's because the light was constantly being scattered by the free electrons, which is similar to if you're in a dense fog, not being able to see very far. And the idea is that around 300 to 380,000 years after the Big Bang, or sometimes you'll see 350,000 years after the Big Bang, the universe cooled enough for the atoms to form, so-called recombination. And then when the electrons were bound to the nuclei, they were not able to scatter the photons as effectively. Basically, the cross-section for interaction was vastly diminished, and the universe became transparent. And then the CMB that was discovered by Penzias and Wilson is this remnant from 300 to 380,000 years ago. This was first really fully confirmed, we could say, by the Cosmic Background Explorer, or COBE satellite, which was launched in 1989. And it was able to get a full sky picture of the CMB, and in particular was looking for very little variations. So even though Penzias and Wilson found that everything was isotropic and exactly the same, because there are galaxies, there is structure in the universe, we expect there to be small, small deviations that were really the seeds for the formation of galaxies and clusters and superclusters. And COBE did find these little tiny ripples that over billions of years formed really everything that we see around us today. All right, and so last we have our second radio astronomy worksheet. So go ahead and work on that. And then that ends the end of today's class. Again, apologies for posting this apparently quite so late. In the future, if you notice that something is missing, please do email me. Thank you to the student who did email me pointing out this issue. All right, take care.